As an analog designer, do you know what are the basic troubleshooting techniques for spice simulation in VLSI industry perspective? Do you know the setting that can impact your electrical characterization through VLSI spice? Do you know the difference between the .IC and .NODSET settings and how they can impact the VLSI spice? Stay tuned till the end of the video to know all the answers. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, common issues in spice simulation and how we can troubleshoot. Here we will talk about some pointers that you can follow, remember and note down, so that in upcoming episodes we are going to discuss multiple commands and etc. Starting from this episode, we'll go in deep detail of multiple commands, and associated issues are listed up in a lookup table manner in this particular slide. So you get the details later and you get the initial lookup table, what to do when, in this particular slide. Next, we will talk about .option general. We will focus on this particular command that is used inside spice. Next, we will talk about the .option for OP, that is operating point, and DC. Now, OP is a concept that you have from your textbook. The operating point for BJT, you can remember that we have to know the Q point, right? And the DC means whenever a circuit is turned on, it needs DC, and next it can have AC superimposed on it. However, the base level DC have to be addressed to this particular DC command, and we will go in detail of these things. Next is the .option for AC and TRAN. So AC is the AC analysis and TRAN is the transient analysis. Transient is with respect to time. So x-axis you have time, y-axis you will have your waveform, and this type of analysis is called transient. And AC, generally there is also x-axis, but however this will have some frequency and this will have your waveform. Okay, so that's the AC. For these things, you have some options, and these are very crucial options for the simulation. And let me speak, many of the advanced VLSI tools, say whether it is in the ASIC design or it may be some in physical design, right? So there multiple tools may use the spice simulator inside. Another example is the characterization engine that use the spice internally. So that time these options are very crucial. If you do not set them right, you are going to have multiple crashes of spice decks, and you will come to know only once you enter the VLSI. Before that, I cannot tell anything about that. There are these options, the .option general, .option OP, DC, AC, TRAN, all these things will have a great significance and a great impact. That is the reason we are discussing this. And before that, we are having a mapping table right here so that you can have a clear guidance why you are learning this. Next is the element specific .option. We will go for element by element here. Next, we will talk about a NODSET command. There is an operating point, right? There is a similar concept for NODSET. Node basically is the nodal point. So in a circuit, there will be multiple nodes, right? Nodes where multiple interconnection or junction are there among the different circuit components. So these are nodes, and these node values can be set with an initial guess. That means whenever the numerical engines are used, right, they need an initial guess sometime to start their numerical operation. So for that we need some numerical guess, and that is set by the NODSET command. Say there is a crucial node, there is a drain of a MOSFET. So there we set some value, and that will take as the initial guess, and then the numerical engine starts from there and do the rest of the calculation. Those are needed, because otherwise the simulation will run infinite, it will crash, something like that. Unusual behavior will come. So that's why we are talking about these things. Next is the .IC, that is the initial guess, and initial guess and the NODSET, these are two similar commands. However, there are some differences. Once we go in detail, you will find out the differences. So here we will stop in today's episode. In a nutshell, we will be talking about the .option statement, .NODSET statement, and .IC statement in this episode. So that's the menu for today. Without any further delay, let's begin. Common issues and troubleshooting. Whether you are running a spice, directly using a spice simulator, or any advanced spice that are used in today's VLSI industry, there will be issues definitely once you run. Whether you are doing an analog, means a functional simulation, or you are doing some type of electrical characterization, you will have to face issues. That is the reality. And you have to troubleshoot them also. So here in this slide, we'll talk about them, and you will have a mapping of what to do when here. So let's start. First one, the spice is not running. Reason is active spice syntax in the first line of your netlist file. So remember, there is a asterisk and there is a comment in the first line of every spice file that has to be maintained. If you start writing from the first line, your spice, say you are defining a voltage source here, that will not be counted and that can be ignored, and hence the spice may not run at all. So you have to be very careful. Spice run is crashing. You start the spice run, after some time you see it has come out, the simulator has crashed. And what is the reason? The reason is the accuracy or the tolerance setting is improper. Now how the accuracy and the tolerance you have to set, we will come to the later dot options and etc. today. So you see that. And in addition to these particular spice options, there can be some tool specific option that may vary from one vendor to another vendor. Even you have 3 different spice simulator from 3 different EDA vendors. They might have additional tolerance or accuracy settings defined by their own. For that you have to consult their tool manual, not the spice language. The spice language do have some impact, but on top of that, when the simulator is running, they can have their own option to deal with difficult situations. So those will be there. You have to be aware of them and you have to use them properly. Next is the spice run is stuck. So that is the convergence issue. Convergence issue comes from the numerical simulation. That is the, say just for an example I am saying, neutron rhapsody or bisection. So they start with some point, they start to progress, and at some point they cannot converge. So that is the convergence issue. Obviously troubleshoot that. For that we have today's episode, the .option, .NODSET, .IC, all these are there. So we have to tweak judiciously them so that the convergence issue is tackled. So how you will detect what to use? There will be a log file of the spice tool. There will be some warnings, some messages. You have to scan through it. You have to comprehend where the problem is coming, and then you have to accordingly set the major commands that we are going to discuss today. No waveform or output dB. So there is a probe command we have talked about earlier, and in case you give a improper probe command or no probe command at all, this scenario might happen that there is no waveform output database has been come out, even the simulation has finished without any error or warning. This might happen that you have not given a probe command, or you have given a probe command which is syntactically incorrect, or you have given a to probe some waveform that is not there. There could be human mistake, so you have to be careful. Next, the waveform is distorted. Initial operating points are wrong. In today's episode, we are going to talk about the .IC and the .NODSET, right? Those will help in this particular situation to correct the waveform from the initial distortion. And if there is initial distortion, later on, the behavior of that particular wave as per the functionality of the circuit may get impacted. It may show weird behavior that is not expected from that simulator, but that is not functional incorrectness that might come from the initial points. That is the initial point guess. Runtime is too high. The accuracy is too tight than needed. So accuracy here, first of all, is very much tightened. That means you are running a very high accuracy spice simulation. That time, runtime can go too high. There is I said earlier, right? There is matrix calculation that happens inside the spice, right? So for that, every node has been taken care, and each node there will be a matrix, data matrix, right? So those have to be solved in the matrix method and all. Now, if you give a too tight high accuracy, these solutions will take time by the mathematical engine inside the spice, right? And this is the reason your spice run becomes too slow, because you have set the accuracy high, and each point, because it's a dynamic simulation, it's not a static simulation, every time point, every time step, each node, and like this node, everything has to be calculated, and then the time markers moves one time step forward, and again at that point everything is calculated. So if you give a high accuracy, the time for each of these node calculation, right, inside the circuit will go and take much higher time, and as a result the cumulative time will be much higher. As a result, what will happen? The spice run will go slow down, and you are thinking what's wrong. So this is the thing, runtime is too high, your accuracy is too tight, you have given a very high accuracy run. You have to reduce some accuracy. Another aspect is that you have chosen a low-end machine, like in the LSF or UGE, you have chosen a low-end machine where the computational power is less. So you target a high computational power machine through LSF or UGE, right? That can also contribute for this kind of troubleshooting. That is the hardware aspect. However, from the spice aspect, the accuracy is too tight, and hence the run is slower than your expectation. So there is no basic guideline that this run is high, this is low. This is as per your expectation, that the spice run will take 2 hours to conclude, right? And it is taking 2 days to conclude. So that is too high, and the reason is you have given a very high, that is a very tight accuracy. Next point is the dot measure output is blank. The dot measure command is wrong. So there will be a text file which will contain all the results from the dot measure, right? You see it's blank. So that means you have given the measure command wrong. That means either you have syntactically put it wrong, or you are doing a measure over a waveform, right? You have chosen some points which are maybe outside of this waveform, or somehow the calculation that cannot be done here. So you have chosen this time window, which is wrong. So anything could be there. You have to physically open the waveform and inspect what you are doing wrong by going to the first time point and the next time point in between whatever you are measuring. So this is the part where the measure output is blank. So this is the reason. Command is wrong. That means you have syntactically wrong. That means you have written a totally wrong command, or you might have done something wrong in the physical waveform. So you have given the time on T1, T2, in between you are measuring something, and T1, T2 is in at some point where there is nothing to measure. Okay, so that can happen. Next point is error, the file not found. What is the error? We learned about the dot include, dot leave, dot model, right? Where we are pointing to a path which is there in your hard disk in the work area, right? It may be in a physical machine, or it may be in a remote machine you are accessing through your network, right? So there is some A/B/C/D/ like that path in the Unix, and there is something wrong. Say some folder has been removed here or renamed here, and hence you are not getting the file here. So you have to physically inspect that the file not found. So that means there is a problem happened in the Unix system. You have to go in the Linux terminal or Unix terminal, and you have to go to the path, see what is wrong there. Another thing could be you have used a wrong syntax of the dot include, dot model, or dot leave, and hence this error is come. So these are the points which can be the general problems once you are using a SPICE simulation, either for your analog simulation, or you are using a SPICE simulator inside through some EDA tool. So there you are facing issues. So any issues more or less will be coming in this point. You have to be very cautious about this, and you have to take action accordingly. And this is not a very straightforward thing. You have to go analyze, check, come back, and then rethink, and then you have to go again and check. So this way you will reach to the conclusion, okay, this is wrong and this I have to change. So we are done with this particular slide. Let's move on to the next slide. Dot option general. So there will be a few general options for the SPICE simulation. Let us see. This is for the init numerical engines. Okay, so the numerical engines which run in background, right? There is some initialization for them. So we are focusing on those options which are categorized the general option of the dot option. List is the option, and it is used as is. Pauses the summary of listing of the input data to be printed. It's a kind of outputting the details of the dot option. ACCT pauses the accounting and runtime statistics to be printed. So you can see at it will give some data related to the accounting or runtime. No at, that means no printing of statistics, no printing of initial transient solution. So nothing will be printed. List causes the summary listing of the input data to be printed. It gives a summary. Node causes the printing of the node table. So there are internal node, important node. I think those will get printed using the node. No mod suppresses the printout of the model parameters. So whatever options I'm talking about is regarding with the ngSpice, and from one particular SPICE simulator to another particular SPICE simulator, there will be similar options. Okay, similar commands. You have to check the manual for that, but the philosophy remains the same. So you understand the philosophy here for ngSpice, and then you can map to any particular standard industrial EDA SPICE tool, whether it is a basic SPICE, pure SPICE, or accelerator SPICE, or it's a fast SPICE. So anything, there will be some such set of options. Philosophically, they will be similar to whatever ngSpice is there, but how will be there will be some changes maybe in the text or something. So you understand the philosophy here, and you can port it to the actual VLSI world. OPTS, that is the ops, causes the option values to be printed. Temperature equal to X resets the operating temperature of the circuit. The default value is 27 degree, that is 300 Kelvin. Now this is a very important, and this is used in almost every SPICE simulation because we have process, temperature, voltage, three kind of variation for the PVT, right? Now this T, even we have the process file from the dot model and etc. as we have discussed in the last episode, right? The dot model, dot lib, how they are accessed. The temperature is finally controlled here to the SPICE simulation. So P process file comes from the SSTT, etc. Right? I have shown you the model files, how they are included in last episode. The voltage will be given by you as a SPICE voltage commands and options, and the temperature is controlled by this. So this is very important with respect to the VLSI, because the PVT, that is the process voltage and temperature, is important in VLSI, and we have an entire episode on these process corners. These are called process corners or PVT corners or PTV corners. There are many names. Why they are important? Please watch the video. We have the link in the description. Now in this slide, we will talk about the option for OP and DC. OP is the operating point, like similar to the Q point of BJT. I am just giving a similarity. It's not the actual thing that we are going to face here. And the DC. The DC means the basic DC operation of a circuit on which we may superimpose AC, pulse train, any kind of transient operation. Let us see the commands. This is the purpose to impact the numerical engines with the initial values. G min equal to X resets the minimum conductance, that is default is this value. Conductance we know from our knowledge, right? Next, ITL equal to X resets the iteration limit for the DC. So iteration limit is the iteration limit of the numerical engine for the DC solution. Default is 100. Even you can vary this iteration limit up and down, and accordingly you can help with the non-convergence problem. Now again I mentioned these are respective to the ngSpice, and you can have similar options in each of the industrial SPICE tool from one vendor to another vendor. ABS tol equal to X resets the absolute current error tolerance for the program. Default is 1 picoampere. So this much relaxation you can give as for the current calculation error. So this is the tolerance. That means you are allowing the simulator to have this much of error, that is acceptable. You need to relax it or tighten it, that is up to you. Once you run the simulation and you get the results, you can tweak with these options as per your need. Pivtol equal to X resets the absolute minimum value for a matrix entry to be accepted as a pivot. Default is this value. So this is a matrix solution. I have told only, right, that for all the nodes we have matrix and we do the solution to it, right? And this option is to impact that particular calculation. REL tol equal to X. So this is another tolerance that resets the relative error tolerance of the program. Default is 0.001, that is 0.1%. So this is a relative error tolerance. So we give a absolute error tolerance, right? And this is a relative error tolerance. So these are kind of way of allowing the simulator to have some inaccuracies, so that at the cost of the inaccuracy, you achieve your result within time. Or in case you are stuck for a non-moving point in a SPICE, right? The SPICE simulation is stuck, right? In that case, you can tweak these options to move out of that situation. Next is the VN tol equal to X resets the absolute voltage error tolerance of the program. Default is 1 microvolt. So again, this is voltage level tolerance that you are giving the relaxation to the simulator, that you can have this much of relaxation while your calculation is there. So plus minus this value is okay for any value calculation that you are doing. So this is how you either tighten the accuracy or you loosen the accuracy. That means you are allowing the simulator to behave as your wish. So folks, these are the few important settings that you use for your simulation, and these are mainly related to the convergence and all, right? So in case you have a convergence issue somewhere, you can look into these options, what is there and how it is impacting. Obviously you have to read again the log file to get any relevant messages there, so that by using that you can come to the conclusion where you have to change. And again I am saying these are for ngSpice. For any other simulator you will have similar options. They may have the same name, they may have some different name. The philosophy will be the same. So we are done with this particular slide. Let's move on to the next slide. OPTION AC and TRAN. So we have some options for the AC analysis and the transient analysis. So let us see them. This is for the numerical engines for the initial, that is the init value. Hence we are giving a label here, and each slide we have such label. So mind the labels. There is a const step equal to X. So X is the value. This is relative step limit applied for code models. Next is the XMU equal to X sets the damping factor of the trapezoidal integration. These are all related to the numerical calculation, right? Default is 0.5. CHG tol equal to X resets the charge tolerance of the program. Default value is this. These are kind of options that are more advanced. You may require not in the initial stages of your SPICE simulation or result. You may require some later point where you are doing a functional simulation, and there you may require them. Next is the max evita. Okay, so equal to X sets the maximum number of event iteration per analysis point. It's very simple and straightforward. Next one is the method. So this is a numerical method of integration for SPICE. I have talked about the bisection, Newton-Raphson. Those you learned in the classroom book, that is in undergraduate level. However, dealing with the SPICE, the internal methods, the numerical methods, right? What are they? One example is gear, another one is the trapezoidal or trap. It is shortened as trap. So you may see gear or trap. There could be some more, right? You have to consult the manual. Default is trapezoidal. Generally, this is the methods that are used. There could be more number of methods. So you have to consult the respective tool manual, the SPICE tool manual, to get what are the available numerical iteration methods. In case one method is stuck, right, you go back to the initial options that few slides back I have talked, or you can come back and you change the entire numerical method and then see what is happening. So it could be better, it could be worse. So you can do those experiments. However, generally any tool company has application engineers. They will guide you whatever is best in which case. So in case you are stuck, you check with them. Either you file a ticket in the support portal. Their application engineers will reply through which you are filing the tickets. Otherwise, if you have a physical application engineer available in your workplace, that person will also guide you. So these are the things that you know when you are working in VLSI. Because for a classroom simulation, easily it goes, right? But for VLSI, you have to meet the target. That means whatever design target is there, you have to meet, and for that whatever you have to do, you have to do. Next is the TR-TOL, resets the transient error tolerance. Default is 7. The parameter is an estimate to the factor by which SPICE overestimates an actual truncation error. So if there is a truncation error, this will be the parameter to play with. No OPAC. Do not run an operating point analysis prior to an AC analysis. So in some cases, it may be needed. Auto stop stops a transient analysis after successfully calculating all functions specified with the dot measure command. So this is another option to play with the transient analysis. We have talked about multiple options. Those are applicable when you are dealing with the AC simulation or a transient simulation. In SPICE, what is the AC simulation? We have a periodic waveform as an input, right? Input vector. And what is transient? Where the output is with time. The time related output. That means in x-axis it will be time and y-axis it will be the waveform. So this way we deal the AC and the transient. AC could be another thing, the circuit which has started oscillating, right? It can output an AC. That is another also option, the AC analysis. We are all done here in this slide. So let's move on to the next slide. Element specific options. So we have some element specific options in SPICE. Let us get familiar with them. Again, these are related to the init numerical engines when the initialization engine is running. All these options are related to that particular engine. So this is BAD MOS3 uses the older version of the MOS3 model with the kappa discontinuity. Since the MOSFET has multiple generations of DC model. So this is one particular option to choose the MOS3 model. DFAD-X resets the value of the MOS drain diffusion area. The default is 0. TFAS-X represents the value of the MOS source diffusion area and default is 0. Next is DEF-L equal to X. Resets the value of the MOS channel length. Default is 100 micrometer. So you can see these three are related to the MOSFETs. DEF-W equal to X. Resets the value of the MOS channel width and default is 100 micrometer. So these all are regarding a MOSFET element and these are not applicable for a BJT. Scale equal to X. Set the element scaling factor for geometric element parameters whose default unit is meters. So this is scaling option. That means what you know about the scaling, right? You know about the lambda, right? In the VLSI technology. Similar things are there. The scaling factor of the MOSFETs. Those are tackled by the scale equal to X. Following instance parameters are scaled. Now, resistors and capacitors, WL, diodes, WL and area. That is the length, width and area. For JFET, MESFET, WL and area, and MOS for MOSFET, WL, AS, AD, PD, PS, SA, SB, SC, SD. So all these things. So these are parameters. Those reside in the BC models, right? And those can be scaled and the scaling control will be done by this. So these are the element specific options. So this way you can tweak them. We are done with this particular slide. So let's move on to the next slide. NODSET. Now we are entering into the convergence issues when we deal with what we change. First one we'll talk about the NODSET and next one we'll talk about the .IC. So they have similarity and difference. So please pay attention. This is for the NODSET. Again, we are having a label. This is for the NODSET IC. That is the initial OP, that is the initial operating point guess. The NODSET line helps the program to find the DC or the initial solution by making an initial guess for a particular node. The restrictions are then released and the iteration continues in true or actual solution. So first, if you tie up a point and from there the simulation starts. So this tie up point is done by the NODSET. This is for a particular node only. Or multiple nodes you can set using multiple NODSET command. The final bias point calculated is independent of the NODSET provided by the guess. That means the Q point, like a BJT, that is calculated and that is separate. But the simulation should start from for a particular node from that point. Basically, we are talking about, right, it's a transient solution and some point we are starting, right? So that starting point in time t equal to 0, we have some particular node that will contain some particular voltage, right? That is done by the NODSET. The NODSET line may be necessary for convergence of bistable or astable circuits. So you know about bistable and astable circuits from your classroom. For those kind of circuitry, the NODSET will come into the picture and play its role. Here are some examples. NODSET, how we use it? V, then node number, then value, then again V, node number, then value. Here it can continue. It can have multiple number of nodes and their values we can set initially in this way. And NODSET all can be there and all could be have same value. It's a global setting, right? You are using. Then we give an explicit example here. NODSET V at 12th node is 4.5 and V4, that is we have a node side. These nodes are defined in the SPICE deck. So there we set 2.23 and NODSET all equal to 1.5. These examples corresponding to this kind of declaration and this example is for this kind of declaration. So this way we use the NODSET command to set any particular node to any particular value for the time t equal to 0 or time t equal to t1, whatever is there from where we are starting the simulation. So at the starting point, some node values will be this and then things will move as per the circuit behavior. This is the thing that we do with the NODSET. We are done here. Let's move on to the next slide. We are talking about the IC, which have a very similar kind of role as the NODSET, but it has differences. Let us see the differences. And again, I am saying that this is for the NODSET or IC initial OP guess. That means the initial operating point guess. The first one is the .IC line is for setting transient initial conditions. Next is you should not confuse this line with the .NODSET line. First thing, here is the line of caution. You should not confuse the line with the .NODSET line. And .IC is for the initial transient condition. So transient means in x-axis there will be time and y-axis there will be waveform as per your design output. For this kind of operation, right, the initial guess, right, the IC will be come into picture. NODSET is for any particular node, right, that you define in SPICE. There you have to set some value. IC is generalized and it's for the transient solution. The NODSET line is only help the DC convergence and does not affect the final bias solution. This is the striking difference. It has two different approach, whether UIC parameters is clubbed with the TRAN control line or not. So either use the .IC or there is a UIC parameter in the .TRAN command, you can use that. When the UIC parameter is not clubbed with the .TRAN control line, the DC bias solution is computed well before the transient analysis. So DC bias solution, that means the initial calculation of the nodes. There will be lot of nodes and in the circuit, right? For each of them, there should be an initial calculation and that is well done by the .IC. If you do not use the UIC, UIC will club it with the .TRAN. In this case, the node voltages specified on the .IC lines are forced to the desired initial values during the bias solution. During transient analysis, the constant on the node voltage is removed. This is another thing. These are some constant. The .IC is a constant just for the initial calculation. But those are removed when the transient analysis is started and it is going forward. During the transient analysis, the constant on the node voltage is removed. That means once the DC calculation is done, it's done. And then you move to the transient analysis and that time these constraints are absent there. The transient will roll in its own fashion. This is preferred method since it allows to compute a consistent DC solution. This method is preferred, right, by the SPICE engineers or you can say analog engineers because it gives a consistent DC solution. We are done with this particular slide. Let's move on to the next slide. We are continuing with the .IC. And again, I mentioned that this is for the initial guess or the OP points. UIC parameter in .trans command tells the simulator to use IC statements globally apply on the capacitor, diode, BJT, JFET, MOSFET initial conditions. So this is the specialty of the UIC command used along with the .tran command. We have not talked about the .tran command. Upcoming episodes we will cover that. Here the DC solution is done along with the transient solution and not independently. So the DC solution, when we are using the UIC, it is getting clubbed with the transient solution. And when we are using the IC and we are not using the UIC, that time the initial condition solution is independent of the transient. For manual override, local IC statement can still be present there to take precedence over the global IC values. So in a SPICE deck, right, there could be global IC command and local IC command. Once you code the SPICE in detail, you will come to these things. Here, theoretically explaining this thing is a bit difficult. Let us see some example. Like .IC, V11 equal to 5, V4 equal to -5, V2 equal to 2.2. This way we can use the .IC, or simply we can remove all those things and we only have the .IC. So in this two fashion, you can use the .IC. These are very crucial things of a SPICE. Even if you use an industrial simulator, the .NODSET and the .IC are very much important, because this will decide how the simulator is kickstarting the simulation. If the kickstart is wrong, then the entire simulation will go wrong. So for that, these are very two crucial points. You have to be very careful about them, and you have to use them cautiously, judiciously, as per the need. Once you consult the log file, you will come to know what wrong has happened, and accordingly what we can change in the .IC or the NODSET. It is not expected that as a beginner you become proficient in using .IC or .NODSET, but over time, or in case you have some experienced person in your company, you can take the help of that person, or you can take the help of the application engineer by filing a ticket in the support website, by telling the situation or giving the log file, right? And this way you will have a working experience. So whatever we have talked here is a theoretical experience, and when you work in a company, you will get some working experience which will be additional to all these knowledges, and those are case specific knowledges. With that note, we are done with this particular slide, so let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislike, please write down in the comment section below, and bye for today.